Recording is rolling. It's Monday, August 29th. So I'm going to do some graphs with you guys and then solve some of these puzzles. I know I gave you guys this page last week and yeah, finally getting around to solving some of these. You guys remember your linear motion homework picking up this Friday. So that's just to solve these problems, which we're going to do some of these today. Right? Now, on the other side of this page are 20 conceptual questions. We'll also do these in time, but your guys' main focus is these graded questions. And I do have a quiz lined up for you guys that I wrote this last weekend. It's mostly geared towards those questions. There's some graph questions on there. There's even a couple of those conceptual questions too from the other side. So I want those too. I want to get that to you guys by the end of this week. That's my plan anyway. Last couple of years, I've been doing take-home quizzes. Ever since the pandemic hit, that's been working out pretty good. So I think we'll try that again. See how that works. I'd ideally like to get started on projectile motion by the end of this week, but we'll see. We'll see how the time turns out. Okay. Oh, also, I'm not going to be here Wednesday. I hate to miss school because I always want to be here and working with you guys, but stuff got to take care of. So, all right, let's get going. First thing here, let's do some graphs. Let's do some constant velocity graphs. Now, I know I did some graphs with you guys that involved acceleration. We did your guys' lab graphs, like rolling the Hot Wheels cars down the incline. We did like dropping a ball off the cliff. Take note of those. Those will be important, but maybe even more basic is, well, what if you're not accelerating? What if it's just a constant velocity situation? Right, so here's a scenario. Get a picture for this and then fill it out. Okay, let's say I got a tree here, and I got this dog sitting by this tree. He's just hanging out there. Let's call it position 0. Call this x equals 0 meters. He's just sitting there. Okay? And then after some interval of time, he notices, oh, there's a squirrel over here, big bushy tail, and like brakes and it starts running towards that squirrel at constant velocity. Okay, then the squirrel notices and like zips past him the other way and runs towards the tree and up the tree, and then the dog chases the squirrel back to the tree and then comes to a stop. Okay, so dog's sitting there for a while, then runs in the positive x direction, then runs back towards the tree. Okay, so that's gonna be the whole story. I'm gonna split this into 3 parts. Okay, dog sits at rest for I'm gonna write this as an interval. Time is between 0 seconds and 10 seconds. 0 seconds and 10 seconds. Okay. Then the dog notices the squirrel and runs at constant velocity towards squirrel. Between 10 and 20 seconds. So 10 seconds to 20 seconds. Okay. It's called the positive x direction. Okay. Then the squirrel's gonna run back the other way and up that tree. There's only one tree in this story. Okay. So then the dog chases the squirrel back to the original tree. Between 20 and 30 seconds, 20 seconds to 30 seconds. Okay, so we got some time intervals going on, right? Okay, so there's 3 parts to the story. Okay. Dog's just sitting by the tree for 10 seconds. Dog's running at constant velocity towards the squirrel for 10 seconds. And the dog runs back towards the tree for the last 10 seconds. Let's say this is also constant velocity. Back to original tree, say, meant to put in that detail, at constant velocity. Okay. But it might be a negative velocity, right? He's running back the other way. Okay. Right. And now I'm going to set up 3 sets of graphs. Now, if you look back in your notes from last week, you'll see the 3 sets of graphs I've got set up here. Also, the same sets of axes that you saw for dropping a ball off a cliff. Right. I don't know if you guys remember that one particularly action-packed day where needed every minute of class. There was one there that involved dropping a ball off a cliff, and we did X versus T, V versus T, and A versus T graphs for that scenario. Okay. So we set these axes for dog chasing a squirrel around. How far is the dog gone in meters as a function of time and seconds? How fast is the dog going, meters per second, as a function of time and seconds? And what's the acceleration of the dog, meters per second squared, as a function of time and seconds? Uh, Here it is. Okay, so we'll dig this up real fast. Okay. I want to remind you a different story. So just so you can kind of compare these, right? This was for dropping a ball off a cliff. You guys remember dropping a ball off a cliff? It was in free fall. There was a constant acceleration. It picked up speed at a constant rate. And then position first time, it's like it went further and further every successive second. So X versus T looked like a problem. Okay. Now, that's a different story, but those were the same sets of axes. Okay. So I wonder how this is going to look compared to that, right? So split this up, intervals of time. Let's go 0, 10, 20, 30 seconds. I wonder if you guys can draw these graphs before I do. Give you guys a little head start here. Because if you guys can draw these graphs, then that means you know how this works. That's a good sign. And if you get it wrong, you just erase it. If I can draw what I draw. If you know what you're doing, go ahead. If you need some hints or right. This is a bit more basic than dropping a ball off a cliff because guys, concept velocity. If concept velocity is the same thing as zero acceleration, ooh, that might be a big hint there. There are a couple of little tricky things to these graphs, but let's see how you guys do that. All right. Well, I remember last time I had 3 graphs like this. I did start with the middle one and then branch out from there. So hey, why not? Maybe I'll do it with those two. Okay. So during the first 10 seconds for velocity versus time, the dog just sitting there at rest. You guys have something like this? The dog has 0 velocity during the first 10 seconds. Just have that, right? Okay. Then no, let's do everything for the first 10 seconds. I guess that's a good way to do this. Okay. Now, I did define the tree as like position 0. So the dog was sitting at position 0 at 0 meters. Okay. I could have defined the dog sitting anywhere, okay. But if he's not moving, he's just sitting at rest, then wouldn't his location not be changing for the first 10 seconds? Okay. Okay. If I define this is position like 5 meters, then wouldn't this line just be just shifted up to the 5 meter mark? But it would still be flat, wouldn't it? Because your position is not changing. Time is ticking, tick, 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 tick. But the position of the dog is not changing, right? Okay. How about acceleration versus time? Well, if you're just sitting at rest for an extended period of time, if your velocity is not changing, isn't acceleration also 0? Okay. Okay, so the first 10 seconds, these graphs aren't really looking that exciting, right? Everything's just zeroed out. Okay. Then, so that covers this first bullet point, right? First 10 seconds, dog's just sitting there at the 0 mark. Okay. But between 10 and 20 seconds, now the dog is running at constant velocity towards the squirrel. Hey, just okay. So what do you guys think the next interval of time would look like for those 3 graphs? Just a little head start here. Constant velocity. It's running at constant velocity. After running at constant velocity, did you guys have something like that for your V versus T? there's a velocity that is constant. Right? So if you point a radar gun at the dog, suppose it says like 11 meters per second. It's 11 here, 11 here, 11 here. That's what constant velocity is, right? Now you might be looking at that jump, saying like, I mean, in mathematics that would be called a jump, right? Can you really like go from 0 to 11? I guess if I guess you'd have to like speed up very quickly, right? So if you wanted to, you could do a very steep connection that's not exactly vertical, but it'd be like pretty close to vertical. Okay. If that's the most important detail, that would kind of be there, right? How about these other graphs? Let's do displacement versus time. Okay. What does this displacement versus time look like during that interval?
Linear.
It is linear, isn't it? Yeah. Did you guys have something kind of like this? Okay. Notice this dog is picking up location at a constant rate. Okay. Do you guys remember this from dropping the ball off a cliff too, that these graphs are related to each other? What property of x versus t, if you guys remember this from last week, what property of x versus t tells you the coordinate of v versus t? Or if you don't remember, see if we can figure this out from scratch. Let's think about units. Do you guys see the slope of this line? Slope of this curve? Slope is rise over run, right? Rise over run. The rise is in some number of meters. The run is in some number of seconds. Hey, rise over run, meters per second. What does that describe? A velocity. Right? Like a speed. Okay? And the fact that the slope here is constant means that this velocity is constant. Ooh, you guys remember how the slope of x versus t tells you the coordinate of v versus t? Okay? In fact, is it the same relationship going from v to a? What is the slope of that little line segment right there? Yeah, okay, so it's constant velocity, zero slope. So what is the acceleration while the dog is running at constant velocity?
Well,
it's also zero acceleration, isn't it? Still zero.
Well, there'd be a jump at the very beginning.
You're right. Maybe at the 10-second mark, maybe for like a tiny fraction of a second, does the dog have to briefly accelerate? Yeah. Right, so I might do something like this. Like the dog, pow, like pushes off and accelerates for like a fraction of a second. And he's like, bam, now he's in a full sprint. Okay. Just back up, maybe a little skinny triangle or something. Okay. All right. Is that all right? Okay. Then at the 20-second mark, I'm saying at 20 seconds, but it might be like a fraction of a second around the 20-second mark. The squirrel takes off the other way and the dog makes an about face and runs back toward the tree. Okay. And then at the 30-second mark, arrives at the tree again. Okay. So finish the rest of those graphs. Dog runs back toward the tree. I'll start with my v versus t because that's how I usually do this. Did you guys have a negative constant velocity like this? Dog's running back toward the tree. That's in the negative direction. Okay. If you like, you could say, well, maybe there's a very steep connection here, not exactly vertical. But, right? If the dog comes to a stop at the tree, then maybe you can do something like that. Is that right? How about x versus t? What's that look like? Yeah, just like back down to where it started. Hey, is that slope negative? X versus t, it's a negative slope, which corresponds to a negative velocity, right? Dogs run back the other way. Now, while the dog is in full sprint, constant velocity, what is the acceleration?
Zero.
Still zero. Still zero. But then to really complete this, what are you guys thinking is happening? Maybe a fraction of a second around the 20-second mark.
Jump downward?
Yeah, it jumps down. It's like that. You can even do like a bigger wedge than this wedge, right? How do I know that? Because you guys know the slope of x versus t tells you v versus t. The slope of v versus t tells you a versus t. But you could also go from bottom to top. So here, let's look at v versus x. Okay. How do you go from v to x? What property of v tells you x? Oh, do you guys see a rectangle right here? What is meters per second multiplied by seconds? what is meters per second multiplied by seconds? Meters? Ah, so this rectangle tells you acquired displacement, like change in just, right? Ah, that tells you like from here to here, right? And then the fact that this is a negative rectangle, ooh, these two rectangles canceling out? Yeah, because he went forward, but then came back exactly where he started. Okay. So translate that story down between these two graphs because it's the same relationship. You guys see a very skinny triangle here?
Yeah.
Do you think that the area of that skinny triangle would represent the change in velocity?
Yeah.
And you think that the area of this negative triangle, same story, change in velocity? But look at this. This change in velocity might be like 0 to 11. This might be from positive 11 to negative 11 meters per second. Ah, guys, what's the difference between positive 11 and negative 11?
22.
22. So do you think that this negative triangle is twice as big as this positive triangle? I think so. And then if this dog comes to a stop, do you think for completion you could just do like bam, like something kind of like that again? Okay. All right, that okay? Dog chasing a squirrel. All right. All right, let's do I want to give you guys some simplified scenarios involving these three kinematic equations. Because remember how this is working. There's 5 variables that we're juggling. Okay, so we're just moving in a straight line. Things might be moving forwards or backwards. Things might change direction. They might be constant velocity, speeding up, slowing down. But everything's just staying along one axis, right? Might be up and down, might be forward, backward. And we've got t time in seconds. We're gonna say what's the displacement in meters. We've got initial velocity and final velocity. Now, if someone's speeding up or slowing down, you might have a bajillion different velocities, but all you care about with these equations is beginning of the interval and end of the interval. And then finally, to tie everything together, acceleration, which is the rate change of velocity. Right? Those are the only 5 variables we're dealing with, right? Okay. Now, these 3 equations can handle it any question I can throw at you. Okay. But a lot of times you can use simplified versions of these. For example, right, if you start from rest, okay, then what does that mean in physics terms? If you start from rest, what am I telling you? That which one of these is what number? V naught is
0.
V naught is 0 meters per second. Okay. Could you guys use simplified versions of these equations given that condition? Okay. But for example, what would x be equal to? As long as you're starting from rest, it just boils down to what?
0.
Oh, yeah, this piece goes to 0. And then what are you left with?
1/2.
Just 1/2 at squared, right? Okay. That could be dropping a ball from edge of a cliff. Remember V naught was 0? Okay. See if I do, here. So just be very simply, just 1/2 at squared, which looks a lot like a parabola, doesn't it? Okay. Or how about the second equation? If V naught is 0, then what can you say from the second one?
AT.
Yeah, V is AT. The speed you pick up to is just acceleration times time. Okay. So sometimes if you're told you start from rest or something's applied to start from rest, right, like for example, you drop a ball, right? Oh my God. Let's solve a few of these. Pretty good Monday morning warm up here. Okay. So for example, what if I tell you that there's a cliff that has a height of 125 meters, and you drop a ball. I want to know 2 things, 2 questions. How much time to reach the valley below? And also, how fast is it crash landing? How fast? Okay. You do need a bit of info that I don't have written up here. Do you guys remember what free fall gravity is on Earth? Yeah, you could say 9.8, or more often than not all around that to about 10 meters per second squared. In fact, if you see either one of those, but extremely close answers. So, yeah, about 10 meters per second squared, right? Give you guys a head start to solve this before I do. Because again, if you guys can beat me to the answer, then that is a good indication that you know how to do this. All right. Did they solve either of these questions? Yeah, we check.
I got 5 seconds to reach it.
5 seconds? Yeah. And did you have fast?
Based on, I think, 5 seconds, I'm going to say 50 meters a second.
50 meters per second. Boom and boom. All right. And see, we can just use these simplified versions to feed them to the. So we're going to go x equals 1/2 at squared. Okay. The word drop means that initial velocity is 0 meters per second. Therefore, I'm allowed to use just those simplified versions, right? Okay, let's solve in terms. Yeah, let's do it. Let's solve in terms of variables, right? Because you could plug in numbers at this point and then just do algebra, right? But you can do the algebra first and solve in terms of variables. Can you cross multiply 2 and divide by a? 2x divided by a is equal to t squared. And then do what to extract the t? Square root. 2x on a. Where x represents the height of the cliff and a represents free fall gravity. Free fall gravity type of acceleration. Let's see what that would be. The square root of 2 times 125 meters divided by 10 meters per second squared. You should get 5 seconds. Okay, 5 seconds. In fact, there's a particular reason I picked this set of numbers. Do you guys remember Paul Hewitt from last week? Paul Hewitt demos? He used almost this exact story. Do you guys remember you walk into a mine shaft with a friend, right? You're, hey, I wonder how deep it goes. Drop a rock, count to 5. Takes 5 seconds to reach the bottom. Well, I wonder how deep it is. About 125 meters deep. How'd you know that? College. You guys remember that? Okay. Watched that too many times now. So he did like the backwards version of this. He says he counts off 5 seconds. Therefore, it must have been 125 meters deep. I tell you 125 meters deep, and you guys back solve, oh, well, had to fall for 5 seconds. Okay, same, back and forth. But the follow-up question is, how fast is the ball crash landing? So you could just pick up from here, just use this one, right? Here, I'm just going to solve this here, right? So the speed it picks up to, we got 10 meters per second squared. It's a right there, 5 seconds, 50 meters per second. Boom and boom. Could you have answered the second question without solving for the time first?
No.
How about the third equation? Let's try it out. Let's apply this third equation. And we know what the answer is already. It's crash landing at 50 meters per second. Let's see if this third equation agrees with that. So we're going to go final velocity squared equals initial velocity squared plus 2ax. I just copy pasted this, right? Okay. Oh, the fact that you dropped the ball means this simplifies how? Yeah, v naught goes away. Okay. Oh, and then if you're solving for vf, okay, let's do the algebra first. What's the one algebra step you need? Square root, yeah. So it's always going to be square root 2ax. By the way, you see this all over in physics. Sometimes you can write it this way. Square root 2gh. Okay? Because isn't free fall gravity a type of acceleration? And isn't the height of the cliff a type of displacement? Like I said. Yeah. So what Galileo experiment, 1589, Galileo's dropping stuff off. How fast was everything crash landing? It was always square root 2gh, regardless of what the mass was, which was kind of the point of the experiment. All right, so let's plug in numbers. Remember, we know what the answer is already. We're just going to see just to solve agree. So 10 meters per second squared, a height of 125 meters. Let's see. I hope we get 50. We're gonna see. 2 by 10 by 125 square root. Yep, that's 50. That'd be meters per second. 50 meters per second. Right? There you go. So there's like 2 paths through the forest to get to the answer. Well, answer the question like how fast is it going? One way is you could use x equals 1/2 at squared to solve for t, and then plug t into this b equals a t, and then solve. You get 50 meters per second. Or you could skip the process of solving for t first and plug it straight into the third equation. You get 50 meters per second that way. It's the same thing either way. Okay. So I was trying to make a point here of if you start from rest, you can simplify those equations. Okay. You know what I meant to do is to do something even simpler, because there's another version of simplifying these equations, which is instead of starting from rest, which is a pretty common thing, what if instead you have 0 acceleration? Or I meant to word it this way: if you have constant velocity. Guys, is constant velocity the same thing as 0 acceleration? Yeah. Yep, it's synonymous. Right. Then acceleration equals 0 meters per second squared. Okay. And let's see how these equations simplify with that condition. I meant to do this one first, but that's okay. Let's do it right now. What does the top equation turn into? If you have 0 acceleration. You guys just see x equals vt. So displacement equals velocity times time. In fact, I can even drop the subscript from the v because there's only one v, right? Because the velocity is never changing because there's no acceleration, constant velocity. Okay. How about the second equation? If a goes to 0, right, that's what you do. A is 0, right? Final velocity is initial velocity. Well, of course it would be because velocity is not changing. So that's consistent. Right? What about the third one? If that a goes to 0, square root both sides, it says the same story again. Okay. So these bottom two equations don't really, they're not really good for much other than like verifying that, oh yeah, velocity is the same. But the top one just boils down to this, doesn't it? And then if you have any two of these, couldn't you solve for the third? Let's do a quick example here. Suppose you need to go 100 meters and you need to get there in a hurry. Let's say you've only got 20 seconds to get there. Okay. Can you guys solve for how much time that would take? And what's the answer to that?
Very sure 20 seconds is not a velocity.
Good call. Yeah, good catch. Thank you. Yeah, that should be meters per second. Sorry about that. You guys fixed my typo in your notes. Should be meters per second. All right. So the meters cancel, seconds switches back up on top. You guys see that's going to be, takes you 5 seconds. I forget what I just said. Okay. Okay, here. Let me go back here. I'll leave this exactly like this. Okay, so you got 100, you have to cross 100 meters. It's about the length of a football field. Okay. Let's say you're running at 20 meters per second. I guess that's what I meant to say. You're running at 20 meters per second. How much time do you have to get there? You have 5 seconds. That's 100 divided by 20. Right? Okay, you guys good? So constant velocity, you have any two these, you can solve for the third. All right, you guys ready to solve some of these problems? All right, so I gave you guys this page last week, and I want you to do all 10 scenarios here. There are 10 scenarios, okay? And so let's look at a big picture, like how this page is organized, and then jump in and start solving some of these. Okay, so you guys notice that each of these scenarios has some boxes, but like a table. And I gave you 3 of 5 values for every single one of these scenarios. You guys see that? Because there are 5 variables that it could give you: time, displacement, initial velocity, final velocity, acceleration. Okay. And okay, you guys can kind of see that these three formulas could answer any of these questions, right? Hey, if I let me make up some weird example. Right? If I said you're in a car and you're going 30 meters per second, and I say, well, how far did you go? But the only thing I told you is you're going 30 meters per second. Is that an answerable question? No, because you have to know, well, how much time was it going for, right? Or is that 30 meters per second? Is that constant, or are you like hitting the brake while are you accelerating? Okay. So what I'm trying to get at is, how many pieces of information do you think you have to solve any of these questions? Well, how many do I give you over and over? Okay. Yeah, three. You guys see that 3 boxes are continuously filled? Okay. Now, maybe it's a bit generous because sometimes there's a number that's implied. Like, for example, if you say you drop a ball, guys, whenever you say you drop a ball, what variable are you implicitly being given? Initial velocity is 0, right? Or how about this? If you throw a ball straight up in the air and it rises to a maximum height, what is the velocity at that maximum height? Yeah, also 0 meters per second. So you might call it like final velocity 0, right? Okay, so that's a big picture. Think about way to solve these. All right. And then if there are 5 variables floating around, and I have to give you 3 to be able to solve it, then you could solve for the other 2. Do you guys see a pair of questions per scenario? That's why there are 10 scenarios, but 20 questions. Okay. In fact, about combinations from probability, these are sort of the only 20 questions that you could ever be asked. Okay. Now, the first scenario is the only scenario on this entire page that has 0 acceleration. It's the only constant velocity one. Right? And you guys know constant velocity. Well, we just talked about that. It's going to boil down to this, isn't it? Right? Actually, you know what? What we just solved right here basically is the answer to the very first question. Right? So maybe it's just use the same paper, right? Because the very first question, I told you that there is a plate and a mound, and there's a pitcher throwing a ball from the mound to the plate. Okay. Now the mound to the plate distance, well, that's a fixed distance. In American units, it's like 60 feet 6 inches. But since we're doing metric, we're going to call that x equals 18.4 meters. Okay. And this ball was thrown at some velocity. Okay. And I did give you the velocity for this one. So velocity equals, see on my page, it says 43 meters per second. So I'll go ahead and stick with that, 43 meters per second. Okay. And that's basically a constant velocity situation. Now, simplifying a little bit, it's a bit of an approximation, but it's pretty close to true. We're up here in a blimp. The baseball looks pretty constant velocity across. We're going to ignore the vertical motion, which isn't very much, and the air resistance and all that. Right? And the question is, how much time does the batter have to react from here to here? How much time? Can you guys solve that? The answer is almost up here, isn't it? Just different numbers. So x equals vt. Solve for t. Isn't t always going to be v on x in terms of variables? Right? Or sorry, x on v, I meant. T is equal to x on v. And so it goes 18.4 meters at 43 meters per second.
42.
Sounds about right. Yeah. 0.428 seconds. Like that. So around a little bit. Something like that. A little less than half a second. Or you could have turned this around. I remember baseball games. My brother was trying to figure, hey, I wonder how fast the pitcher's pitching the ball. So we broke out stopwatches and we're timing how long did it take. If you know the fixed distance and the time, could you just divide those two and then get the V? Okay, that pitcher's thrown. Ooh, that was a kind of a slow one. I bet that was a curveball. Okay. But there's a follow-up question. And the follow-up question says, what speed is the ball crossing the plate? Okay. Well, if you throw the ball at 43 meters per second and it doesn't speed up or slow down, then does it also cross the plate at 43 meters per second? Right. Yeah. So that was real straightforward. Let me pause this. All right, recording is resumed. All All right, so we're left off there is if acceleration is 0, just boils down to this. There's no change in velocity, so velocity is the same. So you guys get on number 1, number 2. All right, I'm going to skip down to number 5, number 6. Okay. So because this one's a little bit more straightforward than some of these other questions. Okay. A ball is dropped from a treehouse. It reaches the ground in, hey, this amount of time. Okay, so somebody brought a stopwatch, dropped a ball from a treehouse, takes this amount of time. Okay. We know the free fall gravity. On this page, I did print 9.8 meters per second squared, so we'll use that. I wonder what the height of the treehouse is then, and what speed the ball is crash landing into the ground. Let's do it. So we got number 5 and 6. Start with how tall is the treehouse? Now I can use the simplified version of this because the initial velocity is 0 meters per second, because this is the ball is dropped. So 1/2 gt squared. So we got 9.8 meters per second squared for free fall gravity. My page says 0.9 seconds. Don't forget to square the time. All right. So it rounds to about 4.0 meters. Did that? Yeah. Okay. 3.97 meters. That looks good. 4 meters. Okay. And then the follow-up question, how fast is it picked up to? Okay. Well, if initial velocity is 0, it just boils down to AT or GT, free fall gravity. 9.8 meters per second squared. 0.9 seconds. 0.9 seconds. Okay. Bring it up to 8.8 meters per second. There you go. Okay, so everybody has a different page, different numbers. Okay, so my numbers are different from your numbers. Because everybody's got different numbers, right? Right. I guess there's a small chance you might have my numbers. Okay. But it's the same scenario and same questions, just different numbers, right? Okay. Guys good? All right. How about also want to do where is it? Okay. Let's do the one to skip. Number 3 and 4. 3 and 4. A ball is thrown toward the ground from a treehouse and reaches the ground in some amount of time. What speed was the ball thrown, and what speed is it crash landing on the ground? Okay. All right, so a couple of changes from what we just did. Okay, this one's a little harder, but not that much. Okay. One is that we're throwing it instead of dropping it, so got to break out the full equations. And the other thing is we've actually measured the height of the treehouse. Okay. Right, so see, I don't know either of the velocities, the initial velocity or the final velocity. So let's go equation shopping. So if you don't know either of the velocities, but you know everything else, which is a good equation to start with? First, second, or third?
First.
The first one. Yes. Okay. Because if you pick the second one, there's 2 unknowns. If you pick the third one, 2 unknowns. I guess you could do some crazy system of equations, but yeah, the first one's a lot more straightforward. And what we're going to solve for is what is the throwing speed? Okay. How fast are we throwing straight down? Because you know everything else. Okay. You guys got that? Okay, let's try that. So you got x equals b naught t plus 1/2 a t squared. Okay. We're solving for this, and we should have everything else. I'll go ahead and plug in the numbers first. We'll worry about the algebra later. See, numbers on this page. I got 9-meter tall treehouse. The time to reach the ground, still 0.9 seconds. So this must be a really tall treehouse. Plus 1/2, 9.8 meters per second squared. 0.9 seconds being squared. Okay. Now I should say too, that signs matter, like positive and negative signs. Should any of these numbers be negative, or is it okay to leave all these numbers as positive values? well, let's see. Let's go through one by one and consider here. Maybe I've got a picture going on here. So think about this. Let's visualize this. Okay. We are going forward in time, so we'll leave time positive. That's almost always the case. Sometimes always. And then think about the directions of these things, though. See, I chuck the ball straight down, and also gravity's pulling down, and also the ball moves down. So the fact that the ball is thrown down, moves down, gravity's pulling down. Hey, if I define down as the positive direction, I could just leave all my numbers as positive values, couldn't I? Right? See, if I did something like if I threw the ball upwards first, which is some of these other scenarios, I have to think, I'm throwing it opposite of gravity, so I have to consider a negative sign. But this one, all the numbers can be positive. Okay, so let's see what all this fun stuff is. What is it? 0.5, 9.8, that's 0.9 squared. It's 3.969 meters. Okay. All right, so couple algebra steps. I need to subtract this over. So 9 meters minus 3.969 meters is equal to V naught T. And then divide both sides by this time. Is that okay? Let's try it out. What is look at this many meters per second. Yep, that's an answer choice, so it looks pretty good. Okay, now that's the throwing speed. Okay? That's how fast you're chucking that straight down. Okay. The follow-up question is, well, how fast is this ball crash landing? Okay, so if this is V naught, then what's this VF? It should be faster. Okay, it's got to be faster than this number. Now, at this point, you got some options. Okay. Couldn't you pick either of these last two equations and solve it? Okay. The second equation is in terms of this falling time. The third equation is in terms of the height of the treehouse, but they should both get it for you, right? Okay. Here, I'll pick the second one, see what the answer is, and then real fast do the third one. So final velocity, which we're solving for, is equal to initial velocity, which is this number, plus gravity times time. Okay. So we got 5.59 meters per second plus 9.8 meters per second squared times 0.9 seconds. So what do I get here? That looks like 14.4 meters per second should be the crash speed. So if my choice looks like that, yeah, I see when it looks like that. Looks good. Of course, the other way you could have done that is you could have used this third kinematic equation. So I'll just do this one on the calculator screen. Okay. So you know the throwing speed is 5.59 meters per second. That's going to go there. So I have to square that. Squared. Right? Plus 2 times 9.8 meters per second squared times the height of the treehouse, which was 9 meters. Okay. Now that's all equal to final velocity squared. So the last algebra step on my calculator is to do what to both sides? Square root it. That'll undo the square, right? So if I do the square root of that, you guys know on this calculator, hit second in the negative key, it'll bring up the last answer. Okay. So again, square. This is one way to do it. 14.41. It's the same thing. It's the same thing. Okay. So to pass through the force lead to the same answer. You guys right? Okay. What do we got? About a minute till the bell. Okay. Well, I guess that's about all we've got time for today then. Who's got any questions? Any questions? All right. So I will upload this to Google Classroom pretty soon, and yeah, all your classmates that. All right.